This rate function, the red function, rate of change of sand as it unloads from a truck onto a scale. Okay, can I have everyone's attention, please? Can I have everyone's attention, please? I still hear talking. Okay, please stop talking. Ready to start? So your conversation with your neighbor, you think that's fine, that's not going to be very loud. But if everyone does that, then no one can hear anything, okay? So this is this rate of change function is the red function. And then we're showing a approximate accumulation function for moments of 0.4 seconds. Moments of 0.4 seconds. And we've been working on this equation over here, which based on our delta x, a starting value for which we're going to start accumulating at. And what else? And the rate function, we were coming up with an approximate accumulation function. We know the rate of change at every moment. We want to know how much we have at every moment. So let's just start by, can you give a rough sketch of what this approximate accumulation function will look like based on these moments of 0.4 seconds, which are shown as constant rates in blue there. So based on the constant rates that are blue and moments of 0.4 seconds, could you sketch what the approximate accumulation would look like? Take a minute and see if you could do that. What would the approximate accumulation function look like for moments of 0.4 seconds? What's that? Yeah, but in terms of sketching this, that doesn't matter. Okay, so in the second half, the rate function is decreasing. Does that mean the amount of sand is decreasing? Oh, good, lots of no's. All right, so chorus is no's. Good. All right, so it's just going to, what, keep increasing, but at a slower rate. Okay, so this is what you should have come up with. Faster rate still, slower rate, slower rate, slower rate. This is what you came up with? Okay, so this is the idea of just, can you look at the rate function and come up with a general sketch, a rough sketch of the accumulation function? Okay, so now I have some questions similar to last time. I'm going to ask some questions about what you see over here on the right. But now, instead of focusing on the independent variable, we're going to focus on the accumulation function. So I'm going to, is this the right? Is it? Here, there, sorry. Okay, so I'm going to show you some different things. Question? Oh. So here I'm drawing your attention to these question marks. Again, what are those values? How would you represent those values by those question marks? And then what are those things, like in a phrase that you would speak or write? Okay, so how would you represent those values? And what are they? Go. Okay, so what do you think? So let's start with question 2 first. What are those things in general? How would you describe what those quantities, what those values are? Yes, sir.
Is it the accumulated quantity at the point on the x-axis? Like that's what the accumulation needs to do?
No, it doesn't.
Like
So what I'm showing you is amounts here. There's an amount from here to here, from here to here. There's 1, 2, 3, 4, 5 separate amounts shown as segments, lengths of segments on the y-axis.
Is it the total accumulation?
Nope, it's not the total accumulation at those points. Somebody else, yeah.
The sum of poured
Sorry.
sand. Oh, is it the sum of poured sand for each individual interval?
Sum of poured sand for each individual interval. Okay, getting closer. Did you want to try? Yeah.
Is it like the integral of 0 to 0.4?
No, nothing to do with integral. Yeah.
Completed interval?
What about okay, so these are about the complete intervals. What about the completed intervals? Delta x for the completed intervals. No. Yes, sir. And
The change in y for each completed interval?
the change in y for each completed interval. And what is a change in y in this context?
The amount of poured sand for each interval.
Pounds, right? So weight. So yes, it's an accumulated weight of sand in each completed interval. In each complete, so for this first complete interval, you get that much accumulated weight of sand. For the second completed interval, you get that much. I'm going to do this on the screen. First completed interval, weight of sand. Second, weight of sand from the second. Weight of sand from the third. Weight of sand from the fourth completed interval. And then weight of sand from the fifth completed interval. So this is the individual. And so where do we see that in our A function? Each one of those question marks is what? What would you put a circle around? Each individual question mark, you'd put a circle around. First of all, right or left? Left, okay? The whole left? Just the rate? Nope. It'd be, this is what each one of those question marks is one of those for a completed interval. Rate times change in x, which is an accumulated amount of sand for each completed interval. Does that make sense? Yes. Thank you. Next one. Ready? Go. So I'm showing these there's actually two things to answer, okay? There's this question mark and that question mark, which is the same as the coordinates of this point. Okay? So these two lengths are the same as the coordinates of this point. There's two things to talk about. Go. Okay, somebody new. What do you think these two values are, or the coordinates of this point at any given time here? Somebody new. Yeah.
So it's the weight of sand in respect to time.
Okay, which weight of sand? Okay, pounds, but which pounds of sand is it?
Accumulated weight.
All the sand?
All the sand being poured.
What's that?
All completed intervals.
So it's the weight of the sand from
All
All the completed intervals only, right? So this is the accumulated weight of the sand from completed intervals. That would be this. Are we talking about this one here or this one here? So the x-coordinate or the y-coordinate? The y-coordinate would be all the accumulated weight of all the accumulated weight of all the sand from the completed intervals. What is this question mark then? How would you express that value right there? Say it, someone said it. Left x. That's what this is. It's left x, right? It's the starting value of x for the current interval, which would be also the x value at the end of the last completed interval. So this is left x, and this is all the accumulated weight of sand from the completed intervals. And so what part of the equation is that? Does it have to do with the right or the left? The right or the left, what we're looking at? The left. What about the left is this quantity right here? No, but what about this equation? It's the whole thing. This right here is the y-coordinate of this point that we're highlighting. It's this value right here. It's the total weight of sand accumulated from the completed intervals. So it's summing them all. It's summing up all the individual amount of pounds of sand from each of the completed intervals, summing them all up. Okay, go. Okay, how do we represent this horizontal quantity right here? dx. This is dx because this is concerning which interval? Current interval. What about this right here? Okay, but we never talked about dy. What is this thing here? What's that? Go ahead. The current interval is not a quantity, right? It's not a value. There's a value that I'm representing there with that vertical segment. What value is it? Somebody knew. Yes, sir. The amount. Okay. What? Pounds. The pounds of sand that's been poured in the current interval. The pounds of sand that's been poured in the current interval. So does it have to do with the right or the left? Right. Now we're talking about this. We're in the current interval now, right? And so this vertical segment, what part of this is that vertical segment? How do we get that value, that's the question mark, from this? Just r of left of x. Is that what it is? A few people are saying it. It's the whole thing. Why? Because it's a pounds of sand. It's a pounds of sand. The whole thing is the accumulated amount of sand in pounds in the current interval. Constant rate times the change, dx. Constant rate times the change gives the added amount. One more. Okay, how do we represent each of the two values by the question marks, and what do they mean? Go. Okay, somebody new. How about horizontally? So this horizontal segment here represents what value? How do we represent it? What does it mean? Somebody new. That should be an easy one. She's asking, is it X? And we call it the current value of X. The current value of X. It's our independent variable for both functions, for both the rate function and the accumulation function. So it's what? We know the rate of change at every moment. And we want to know the amount, the pounds of sand at every moment. That's what X is. At every moment. At every moment. That's what X is. At every moment. Okay? And what about vertically? What does the length of that segment represent? In the context. What is it? Joseph? Total amount of sand accumulated in pounds. That's what it is. And how to represent it? How can we represent it? A of X. It's the whole thing. This is summing up all the pounds of sand from the completed intervals plus the pounds of sand in the current interval. Total them all up, and you get the current amount of accumulated sand in pounds for the current X value, which is our time, right? Okay, is this helpful? Watch the video, okay? Review it again. So now, the moment we've been waiting for. We've been working hard for this very moment. What was our goal all along? Yeah, so we don't, approximate accumulation is nice, but it's approximate. Okay, so here is, I've got the delta x moments at point 3 now. Delta x moments at point 3. How does our accumulation function compare to what we had before with moments of 0.4 seconds? Better or worse? Better. So it's clear that by taking more smaller moments, we get what happens to our approximate rate function. It's going to get more accurate. It's going to replicate or try to pretend to be the real rate function better the more smaller moments that we take. So let's see that in action here. So this is 0.3. So I can just click here and say, here's delta x of 0.19. So this is for delta x of 0.19, and then I can even make them smaller. 0.0876. And so what's happening to our approximate rate function? We got more little steps that are now doing a better job pretending to be the real rate function. And then what happens to our approximate accumulation function? It's getting to be more exact to this accumulation function that we've only can imagine so far, right? We only can imagine that there was some real accumulation function for the rate function. And as we take more and more smaller moments, our approximate accumulation function, it's better and better. Okay, so is that the actual rate function there? No, but it's still a step function, meaning those are all constant rates. But it's sure looking a whole lot like the original function. So let's go as small as 0.005. here's 0.005. Those are still a bunch of constant rates over there on the left. But in the back, can you tell the difference between that and our original red rate function? So we've got a very, very close approximate rate function. Let me zoom in here and I'll show you. So still constant rates. We're just taking very small moments now, or actually realistic moments, right? We said a moment is a very short time for which we consider the rate of change to be constant. I pushed the wrong button. Sorry. This is the one I want. Okay. And one more time. Okay. So when our moments get small enough, we still have constant rates, but it's those constant rates all put together are virtually indistinguishable from our original rate function. And to your eye, it looks like a nice smooth curve, right? And so we say when our moments get small enough, we've essentially preserved the original rate function, and then the resulting approximate accumulation function is indistinguishable from the exact rate of change function. Okay, so this is awesome, and that just only took like 5 minutes, right? So we spent 2 weeks building up that function, and then in 5 minutes we can just make delta x really small and say we've got something that's virtually indistinguishable from the exact accumulation function, which is what we want. Given we know what the rate of change at every moment is, we now know the total amount at every moment. It's just a matter of making delta x, our moments, small enough. Okay, so let's look at some notation for this now. Okay, so we got approximate and exact accumulation. Okay, so we have our R sub f function is our rate of change function, and what we're going to call, so our approximate accumulation function we call A. And that's what we worked hard on the last week and a half. So now when we let that delta x be very, very small, we would then get a bunch of so many constant rates that are so small that it would virtually be, have recreated that original red function. And so our new notation for that is integral notation, okay? And so this is our exact accumulation function, starting from x equals a, accumulating to a final value x. Okay, and so how do we read this? How do we read this? So that this is then the black function here. Why does it make sense for this one that our approximate accumulation function ended up underneath the exact accumulation function? Yes, sir? Okay, that won't just because we're using the left sides won't always make it less. So what's happening over there that makes it less? Can you say more? Okay, yeah, so in the beginning, in the first half here, the rates that we're using to make the approximate accumulation are all how compared to the actual rate? They're smaller. All those constant rates are below the curve, so they're smaller rates. So the actual accumulation of weight is going to be greater. And then the second half, it reverses, but now our real accumulation function has a head start, right? And so then it takes the rest of the way kind of for our accumulation to get caught back up again, our approximate, get caught back up. Okay? So this black curve then is what we call a sub f of x, and the meaning of this is it's the accumulation of changes in f due to its changing rate of r sub f of t at every moment t from a to x. Okay, so we should mention what f is. Okay, so f would be generically just this quantity function of pounds. Generically, this quantity function of pounds, which could include pounds for values before a. Okay, then the a sub f function is an exact accumulation, but necessarily beginning accumulating at x equals a. So just if we think universally of a weight function that doesn't depend on where we start accumulating, that's f. That's f. But then our exact accumulation function a sub f means we're going to start accumulating at a. So it's based on f, but it's going to start accumulating at x equals a. And in this scenario, that a was 0, times 0. Does that make sense? Okay. So f is the generic universal quantity function for all values of x. A sub f of x then is based on that when we start accumulating at a. Okay, so what do we see in this notation that still represents this idea that we've been working so hard on? So it's much more compact, but it still has, still preserves all the meanings that we've been talking about. Okay, so we said a was what? The starting value. Starting value of our independent variable at which we're going to start accumulating. Okay, so make sure you know that's the that's not an amount of accumulation. That's the initial value of the independent variable at which we're going to start accumulating. Okay? And then so what does x represent? Yeah, and so it's a function, right? So again, we want to know how much we have at every moment. So that's that's the current value of x. And so at any given x, that's the final value. Again, that's a value of x. That's not a value of accumulation. That's a value of x. So it's independent. But then this is a function, so that thing changes. That thing, like we've been watching over the last weeks, that thing changes and increases. So we get the accumulated amount at every moment for any x that you want. Okay, what else do you see that is representing these meanings and that we've been working on? So what letter does that look like right there? It looks like an S, right? And that's actually German S. And just like sigma was Greek for sum, this integral sign is German for sum. It's the German S. And we're using that again for sum. Sum. And what are we summing up? What are we summing up? Okay, we're not summing up intervals and we're not summing up x values. We're summing up
all the changes in a as x is
changes in our dependent quantity. amounts of accumulation. Okay? As we go through all the intervals. Okay, so as we go through all the intervals. Okay? So the intervals are so small now that we don't have to distinguish. We don't make this distinction between the completed intervals and the partial interval. It's just they're all super small intervals, and we're gonna just move through each one, and we're gonna accumulate the amount through each one. And so, how do we see that as an accumulated amount right there? How do we see an accumulated amount there? Yeah, go. Who said it? Go, say it loud. Constant rate times a change in x. Constant rate times change in independent. dy equals m dx. So we see it there. We still see it there. M dx. And then we're going to sum them all up. And that's going to give us the total accumulation. And we're going to start from x equals a all the way up to x. And that's going to give us our total accumulation. And that's going to be our exact accumulation function. Anybody have a question? So do you see how it's still this notation still has all these meanings that we've been working on the last couple weeks? Okay, so you notice, though, that we have this new symbol t in here, which doesn't mean time. It could, but it doesn't mean time. It's just a new symbol that we need here instead of x. So the question is, why this different symbol? Because so why the new variable? Why can't we just use x there? They're x quantities. We want the rate at an x value and a little change in x value. So why the new variable? Why the new variable? Okay, well, listen. You want to give it a shot? Yeah. Yeah, no, so okay, so it doesn't have to be time. Our independent variable doesn't have to be time, and we could still use the symbol t, and it wouldn't necessarily mean time. So yeah. Right, okay, he's got it. So let's investigate this. That's right. Let's investigate this. Why do we need a new, if we've got that variable x, why do we need another variable that means x values, right? This t, it stands for x values, and dt is going to be a small change in x. Why do we need this new variable t? So I want to show you that in graphing calculator, here's how you can do these integral symbols in graphing calculator. Okay, so there's our a function, and so what happened? Lost everything. Okay, try it again. Control Shift I from a to x, capital R of t dt, and there's a number. Okay. So I get this number, 4.64603, as the accumulated amount of weight of sand at 1.8 seconds. So now this one, alternate version, instead of using the t's in there, I'm going to use x. Okay? I'm going to use x, and I'm going to also find, and I'm just going to call that capital G for whatever it means. And I'm going to do G of 1.8. So look at this. I got 1.17. So totally different values. So let's look at what's happening. So what's happening when I put 1.8 in for the independent variable in G? What's it going to do? It's going to go from 0 as our A value to 1.8. And what's it going to do? It's going to do R of 1.8 dx. This one is going to go from 0 to 1.8 and keep it as R of t dt. So what's happening in this second one where I used x for all those variables, I'm going to be what? Accumulating all the amounts of sand from 0 to 1.8. And what kind of rate function am I looking at here? R of 1.8. R of 1.8. Is this something like right here? R of 1.8 is that much. And so if I start at 0 and accumulate to 1.8, with this using x, I'm going to be accumulating what? The rate is going to be what? It's going to look like this. It's going to be a constant rate at R of 1.8 for all 1.8 seconds. It's not going to accumulate sand according to our rate function like this. It's going to accumulate that sand according to a constant rate. And so what do we see as the result then? Does it make sense? Much lower, right? It's much lower because all it's doing is accumulating at a constant rate of whatever R of 1.8 was for all 1.8 seconds. So we need that new variable t so that, it's exactly what he said here in the front, so that x changes, we have a changing x value from 0 to 1.8, taking on all these different rates from 0 to 1.8. We still need it to be the rate function from 0 to 1.8, not a constant rate of R of 1.8. And that's what you would get if you did R of x dx. So this reflects the actual rate function changing according to the profile of the rate as x changes from 0 to 1.8. That's why we need a different variable there. X means the ending value, the current value of x at the end. And then in between that, if we're going to accumulate, we need all the different rates in between. So we need a new variable representing that changing rate, or allowing for the rate to change. If we just plug the final value of x into the rate function, we'll get a constant rate for that whole time. Doesn't make sense. Okay, so I got some in the last 5 minutes here. Let's see. So again, how do we read that thing? It's the accumulation of changes in f due to its changing rate r sub f at every moment t from a to the final value x. So t is going to take on every moment between a and x, and that gives us the actual rate function that we will accumulate at. Okay, so here are some expressions, some integral expressions, and for each one, or maybe a couple of them, we want to determine, first of all, if it represents a valid accumulation for its rate function. And then we want to identify all the parts of the expression by their meanings. And then we want to introduce function notation to rewrite it as a definition of a function. Or is it the particular value of the function's dependent variable? And then describe the meaning of this expression as a whole. So let's look at this first one here. I've got the integral from 4 to x of g of t dt. Okay? So, is it a valid expression? Will it come up with an accumulation function that's valid? Sure, and the reason is because we've got a different variable for representing every moment between 4 and x. Okay? So let's identify the parts. What is g of t? Rate function. It's the exact rate of change function. Okay? What is g of t dt? G of t dt, what does that represent? Is it the whole amount accumulated from A to X? G of t dt?
Same concept.
Go ahead.
It's the amount accumulated from 4 to t.
From 4 to t. It's the amount accumulated from 4 to t. Is that right?
Or X.
Is it? No. So what this is our moments are very, very small now. And we're summing up the little amount accumulated in every moment. So this is just an amount of accumulation from one moment. And just like the summation sign that we had in the approximate accumulation function was adding up all the accumulation from all the completed intervals, so now we're the summation, the integral German s, sum up all the accumulation from every moment. And gt dt would represent the accumulation in one moment. In one moment. And so we have a zillion of those. Imagine you have a zillion of those, and it's a little, super small, a bit of accumulation, and then we're going to sum all of those up. So it's very similar to summing, Greek sigma, summing up amounts of accumulation. Yeah?
Would it be wrong to say that the moments in question are infinitely small using intervals?
So we're considering, they're small enough to be indistinguishable. So we're still thinking about an approximate accumulation function with very, very small moments, but they're just small enough so that it's indistinguishable from the exact accumulation function. Does that help? Because you can't infinitely small. You still have to have some little width there, right? That's our idea of a moment. A moment is going to be some small change. So you still have to have a small change. And so it's just now we're small enough that when we sum them all up, it's indistinguishable from the exact accumulation. Okay? And so we said that sum, we're starting at x equals 4. We end the accumulation at x. And then that whole thing gives us the accumulation starting at 4, ending at x, of a quantity whose rate of change is g. Okay, so we'll pick this up. We'll put this as part of the homework for Wednesday.